Here we have a program to solve the implementation of the explicit forward time-centered space method to solve the advection equation for a particular case where we have a one-dimensional square wave, as we'll see later. So first here we are defining the parameters that define actually the advection equation and the range in space and time that we want to evaluate and make the numerical evaluation. So the maximum longitude we are going to consider here in this case is going to be 1. And the maximum time is going to be 1 as well, from 0 to 1. And the advection velocity, so the c parameter entering the equation, is going to be 1 as well. Of course, we can change everything here as we wish, depending on the equation that we have to solve and the requirements of the system. I mean, the maximum length, the characteristic length of the system, or the maximum time that you want to consider for the calculation. Then here we are going to present and define some parameters that are needed to implement in the FTCS method. So first we do have here the number of time steps that here we have considered to be 3000 arbitrarily. Then we have therefore the time step, and the time step, which is delta t, dt, is going to be the maximum time over the number of time steps. Then we have to define the number of space steps, which in this case we have considered 30, because okay, here we have considered that we do not require such accuracy on the space. Then that defines as well the space step, which is the maximum length, L max we have defined before, over the number of space steps. Then another parameter that appears in the numerical implementation is the B, in this case, which is the C times delta T over 2 times delta X that we are going to define so that the numerical implementation is going to be more clear. So now second step is that we are going to define which are the initial conditions. So basically it's the initial value of the U function, the initial amplitude of the wave. So we are going to consider like a square step. It's like that. So basically it's going to be 1 up to a certain value and 0 from then on. And we are going to consider that this is the front of the wave, which is the point where the value of the wave changes from 1 to 0 initially. So that's the index in time associated to the front, on space, sorry, related to this front wave we are defining here. So basically we have considered it to be half of the number of space steps, and we are rounding this number because it could not be an integer number, and we want it to be an integer number because it's going to be an index that we have to put in a vector. So as we are saying here, we are going to have a square step, a square wave, and the front initially is going to be the half position in the space. So here we are defining this initial condition, and for that we are going to make a loop on I. I is the index that we are going to use for the space, and that one is running from 1 to the number of space steps plus 1. Just remember that here in a vector component we cannot make a vector component to be 0. That's why we are starting not from 0 as we're saying in theory, but from 1 to nx. So the number of components of the vector that we need to define, as we are considering nx number of space steps, the number of components of the vector are going to be nx plus 1. So here we have, if this I is lower than n front, then the value of the wave at time index 1, so the initial time is going to be 1, otherwise it's going to be 0. At the same time, we are also defining here the vector x. So due to the space discretization, so you are just going to um, consider the x points that are defined here, which are associated actually with the number of the space steps we are considering, and therefore with the space step we do have here. So we are, therefore here we are considering that we are starting from 0 to the maximum one, which is going to be 1. Okay, this after defining initial condition, then we are going to boundary conditions, and the boundary conditions are giving to us the value of the u function at the boundaries at any time. The boundaries are, of course, the x equals 0 and x equals 1. In this case, the indexes corresponding to x equals 0 is index 1, the space, and the index corresponding to the other boundary, to the one on the right, corresponding to x equal L, it's going to be the index nx plus 1. Okay, so again, in this case, k is going to be the index associated to the time, and this one will run from 1, which is going to be the initial time, to the maximum times will correspond to the index nt plus 1. Again, we have the same issue here, as these are going to be the components of a matrix. In this case, the matrix of the components cannot be 0, so the initial one will start from 1 on, and again the number of the k values are going to be nt plus 1, because the number of time steps we do have here is going to be nt. So in order to define the boundary conditions, we have a 4 on the time index, so that we are defining that the u value evaluated on the space index 1 corresponding to the left to any time. So we have k for all these k values, all the k values, it's going to be 1, while on the other hand, on the other side, we have that's going to be 0. That's our boundary conditions. At the same time, we are using this loop in order to define the vector t, that again, due to the time discretization, is going to take just several values which are related with the time step we do have in the problem. So once we have that, then what we have to do is the numerical implementation of the finite difference FTCS method. And here we do have two loops. One is for the k for the time, and the other one goes for the space. So for the space, index will run from 2 to nx, because the index 1 and the other on the other boundary, nx plus 1, are already fixed by the boundary conditions, and this is the implementation of the method. And again, the time will run from 1 to nt, so that using the initial going from already known values of u at a certain time, will be able to get the u values of the next time, and so on and so forth. Okay, this is the numerical implementation for the this method, and after finishing this loop, then we have already calculated all the u values in all the mass in space-time mass we have defined. So in order to see how it looks like, it's interesting to do, for example, a graphical representation of the wave, for example, at different selected times. And that's what we are doing here. We are plotting that different functions in the same plot. For example, we are plotting this one, for example, means that we are plotting the u function evaluated at initial time for all the indexes corresponding to the space. This double dot here, it will give a vector with all the components of this matrix corresponding to the initial time, with all the values of u evaluated at all the space points. And we are going to plot that using a solid line in a blue color. And that's going to be the initial shape of our wave that we do know it's actually the square one that we had initially. But it's interesting to check that we are actually doing it well. So again, the second plot will be here. We'll plot in here this one, the u again, at a different time. In this case, we are choosing the time. This is the time index we have considered as later than the initial time, and we are going to plot it using a different line. It's going to be a green dashed line. Then we are plotting again the u function at another time that closer to the end in this case, but using a blue color and dot line. And finally, we're going to plot the u function we'll have at the end, just using a red color and dash dot line. This is the title, and we are also labeling the x and y axis. So everything is ready, and now we are going to run the program in order to see which are the results. And actually, that's the result that we get. For example, just remember, this is the initial wave that we have. It's a front wave. Then the one which evaluated a bit later, actually, we do know how it should look like. It's a wave, so the shape of the wave shouldn't change. Basically, it should just move, displace. In this case, it should displace to the left. And actually, we can see that the green color, it's also indicating that's a little displacement to the left because it is the one which is calculated a bit later. But actually, you can see that the shape is not maintained. You can see this is moving here, and there is also some oscillation. So you can see that the shape it's actually is not maintained. Then if you go for a further time, you can see that this is the dot line here, and dot line in blue color. Actually, you can see it's much farther from what you would expect, that you would expect something similar to this one. So, and then the red one, you can see it's completely different. It's clearly showing that the system or the method that we are getting here, as we know, actually, it's unstable. So the results that we're getting are really crazy because of the method itself has the problem of the stability. But even though without knowing that the system is stable, if we're guessing that could possibly be a real solution that we could trust, before trusting on others on any solution, as I mentioned before, it's important to change some of the variables that we are dealing with, for example, time step or space step, and see if the results we're getting actually are the same. Because if they are the same, we can start trusting on them. But if they change, of course, then we can distrust on them. So here, basically, what we have seen is we have seen an implementation of the FTCS method, explicit method, to analyze the advection equation, a particular case of the advection equation, where the initial condition is a square wave.